February, March 2025, variance 42, paper 4 of A-level examination. All right, let's talk about the question number 1. Silver is a metal in the D block of the periodic table. Silver can form compounds containing either silver ions or silver 2+ ions. Explain why silver is a transition element. So silver is a transition element because of the fact that D orbital contain electrons or D subshell contain electrons. Also can form one or more stable ion having partially filled d orbital. Since it contains d orbital, which is why it is found in the d block of the periodic table also. All right. Next part, table 1.1 gives data relevant to the Born-Haber cycle for silver 1 fluoride, which is a formula of AgF. So guys, we know the ionization energy of silver, atomization of silver, atomization of fluorine, lattice energy of AgF, and formation. What's not given in this data? Have you observed this? I think electron affinity data is not given. And since it's not given, which means we need to calculate it in the later part. All right. That's the most likely question in this scenario. Write equations for the standard enthalpy changes described. Include state symbols. Standard enthalpy change of atomization of silver. So atomization is a process in which 1 mole of gaseous atom is formed from its constituent elements in their standard states under standard condition. On the basis of this definition, I can write the equation for atomization of silver now. So silver is solid at room temperature and pressure. If you provide energy, it will turn to 1 mole of gaseous silver atom. So 1 mole of gaseous atom is formed from its constituent elements in their standard states under standard condition. Now the next, standard enthalpy change of formation of silver 1 fluoride. So formation is 1 mole of compound is formed from its constituent elements in their standard state under standard condition. So in order to make silver fluoride, I will use silver and fluorine. They will react together, will convert into 1 mole of silver fluoride. Under standard condition, it is solid. Under standard condition, it is gas. And since silver fluoride is an ionic solid, it is also solid also. Now, 1 mole of silver here, silver 1 mole here, silver is balanced. We need to balance fluorine atom. We have 1 fluorine atom here, and we have 2 fluorine atoms here. So I'll put half here. And that's your balanced equation for the change of formation of silver 1 fluoride. Now the next part is define lattice energy. So lattice energy is easy. Enthalpy change occur when 1 mole of gaseous cation reacted together to give 1 mole of ionic solid under standard condition. All right. Let's move on to the next part of the question. Calculate the first electron affinity of fluorine using data from table 1.1. And that was I was expecting. We need to find out the electron affinity. It may be helpful to draw a label energy cycle as part of the working for your answer. And we have only 2 marks here along with this energy cycle. That's unfair actually. Anyhow, let's make the cycle. This is silver ion. This is gaseous fluoride ion. Converting into 1 mole of solid silver fluoride. And that's your lattice energy. Let's make formation when silver and fluorine reacting together, converting into 1 mole of silver fluoride. So that's your standard enthalpy change of formation. Let's put half here. And by the way, this is going to be the delta H1 as per my lecture. And this delta H1 includes atomization of silver, ionization energy of silver. This delta H1 includes atomization of fluorine, ionization, electron affinity of fluorine. All right. So let me make the arrow in the clockwise direction as per instruction. In fact, both these values will take as positive, and it's going to be the negative one, which is going to be the equivalent to 0. So delta H1 plus lattice energy minus standard enthalpy change of formation equals to 0. Now in delta H1, it is atomization of silver, first ionization energy of silver, atomization of fluorine, first electron affinity of fluorine, that's your delta H1, plus lattice energy minus delta HF equals to 0. Let me plug in the values here. Atomization of silver is actually 289 plus. First ionization energy of silver is 732. Atomization of fluorine. By the way, this is the actual atomization of fluorine, which is plus 79. So we don't need to half it because it's not the bond energy value. It's actually the atomization value. Okay. So plus 79 will take as it is. We need to find out the electron affinity of fluorine plus lattice energy. Lattice energy is minus 955, I believe. That was 955. Yes. And minus 203 is formation equals to 0. So when we calculate first electron affinity of fluorine, it's going to be minus 348 kilojoules per mole. All right. Now, C part 1, use the data in the table 1.2 to calculate the enthalpy change of solution of AgF. So in order to calculate standard enthalpy change of solution, I will use the formula which we have discussed in the class. Standard enthalpy change of solution equals to minus lattice energy plus hydration. Lattice energy is already given, which is minus 955 plus hydration of silver ion is given, which is minus 464 plus hydration of fluoride ion is given, which is minus 506. So it's basically plus 955 plus is basically minus 970. So it's plus 955 minus 970. So it's going to be minus 15 kilojoules per mole. All right. So the magnitude of hydration is greater than the lattice energy, which is why solution is always exothermic. And if solution is always exothermic, which means compound is soluble, which means silver fluoride is soluble in water. And that's the next part exactly at 298 Kelvin, right? So use your answer to C1 to suggest whether silver fluoride is soluble in water at 298 Kelvin. Explain your answer. We have 1 mark apart. So let's talk about this. Magnitude of hydration enthalpy is greater than lattice energy hence standard enthalpy change of solution is exothermic. So compound is soluble. So AgF is soluble. Also, due to small ionic radii and strong electrostatic attraction, also called ion dipole attraction, between ion and water molecule. All right. I hope it makes sense to you. Let's move on to the next part of the question. Table 1.3 shows some data relevant to the silver one halide from AgCl to AgI. Look at the data. First electron affinity of halogens are given, and lattice energy of AgCl, AgBr, and AgI are also given. Now, examiner is looking for the trend in the first electron affinities of halogen from chlorine to iodine. And that's easy because we have done this in class, and we know that when we move from chloride to iodide, ionic radius increases. From chloride to iodide. This increases shielding effect also. So nucleus to valence electron attraction vector, less energy is released. So electron affinity becomes less exothermic. Now the next part of the question is explain the trend in the lattice energy of the silver 1 halide from AgCl to AgI. Since silver is a cation and its charge will remain same throughout the trend, which means we need to discuss the trend on the basis of these halide ions. And we know that down the trend, ionic radius of halide ions increases. So down the group or down the trend, ionic radius of halide ion increases. So electrostatic attraction between ions becomes weaker hence lattice energy becomes less exothermic. Let me add one more thing. Ionic radius of halide ion increases, charge density decreases. All right. Let's move on to the next part of the question. Let's see what we have in it. Oh. An electrochemical cell is constructed using the electrodes shown in table 1.4. Calculate the standard cell potential E0 cell. Construct an equation for the overall cell reaction. All right. Now this half cell has a more positive SEP value, which means I will write it down as it is in the reduction form. And since this half cell has a less positive value, which means I need to flip this equation. Now I need to balance the number of electrons. We have 2 electrons here. We have 1 electron here. So I will multiply 2 by this equation so that we can balance the number of electrons. After balancing electrons, we need to cancel out. And the final equation is going to be like this. 2Ag plus 2Cl minus plus copper ions, reversible sign, 2AgCl plus copper. So there's a balanced chemical equation, which I can write it here. Sign will remain reversible. I will let you know about this, why I'm writing here reversible sign, why not irreversible. We have discussed such issues in the class, right? Let me calculate the E0 cell value and then I will explain it to you. So in order to calculate E naught cell, according to my lecture, I'm going to use E naught right minus E naught left formula. In E naught right, we need to put more positive SEP value, which is 0.342 volt. In E naught left, I will write it less positive SEP value, which is plus 0.222 volt. So the E naught cell for this equation is going to be plus 0.12 volt. See, the value is positive, which means reaction is feasible or spontaneous, which means reaction can take place. But since the value is less than plus 0.3 volt, which means reaction never go for completion, right? Which means I need to put reversible sign here, because whenever reaction goes to completion, I will write irreversible arrow. Since it is less than plus 0.3 volt, which means we need to put reversible sign here. I hope it makes sense to you. Let me write down plus 0.12 volt. Whew. All right, next part. In a different experiment, electrode 1 is set up using a saturated solution of potassium chloride. By the way, saturated solution is the concentrated solution of potassium chloride. Saturated solution of potassium chloride contains 36 gram of potassium chloride per 100 cm cube solution at 298 Kelvin. The Nernst equation for electrode 1 is this, whereas Z is basically the number of electrons which we can find out by the equation. And in equation, we have one electron here, okay? We need to find out the concentration of chloride ion by using this value, which is not that much difficult. First of all, find the moles of potassium chloride. So we have 36.0 gram of potassium chloride divided by the MR of potassium chloride, which is 74.5. All right. So the number of moles is going to be, let me check the exact value of potassium, 39.1, I believe. Let's check. 39.1. All right. And chlorine is 35.5. Okay. So 35.5 and 39.1. 35.5 plus 39.1, 74.6. Okay, 74.6. So 36 divided by this is 0.483 moles. So in 100 cm cube, we have this much moles. In order to calculate the concentration, I need to compare the moles with 1000. So in 100 cm cube, it's 0.483 moles. So in 1000 cm cube, the concentration of potassium chloride is going to be 4.825 mole per dm cube, which is also called molar. We have calculated the concentration of potassium chloride, and obviously the concentration of potassium chloride and the concentration of chloride ion would be same because of 1:1 ratio. So let me plug in these values in the Nernst equation. Nernst equation is already given in the question. So let me plug in the values. E naught is given in the first equation, which is plus 0.222 volt. So plus 0.222 plus 0.059 divided by 1. Z is basically the number of electrons. And in this half cell, the number of electrons would be 1 log base 10, 1 divided by concentration of chloride ion, which is 4.825. So the value of electrode potential under non-standard condition would be plus 0.1816. 816. All right. Let's move on to the next question. Propanone is a common organic solvent and reagent. Propanone reacts with methanol under acidic condition to form compound A, as shown by reaction 1. Most likely, this acidic condition refers as a catalyst. So this acidic condition increases the rate of reaction. All right. The overall order of reaction 1 can be found studying experimental data. Okay. That's a very unusual reaction, by the way. Anyhow, let's move on to the next part. Table 2.1 shows how the initial rate of reaction changes as concentration of methanol and hydrogen ion are varied. In each experiment, a large excess of propanone is used. So I've told you in the class, whenever we use large excess amount of any reagent, that means we need to keep the concentration constant so that we can find the order of reaction for these substances or these ions. All right. So here is the data given, and we need to find the order with respect to both these reagents. But first of all, examiner is looking for an explanation in which examiner is asking why a large excess of propanone is used in each experiment. That's a very straightforward answer. To keep the concentration of propanone constant, so that we can find the contribution of methanol and hydrogen ion towards rate of reaction. Okay, next is use the data table 2.1 to determine the order of reaction 1 with respect to methanol and hydrogen ion. Explain your answer. So first of all, I need to find out the order of reaction with respect to hydrogen ion, and for that, we need to make methanol concentration of methanol constant. So these are the concentration constant in experiment 2 and experiment 3. So for hydrogen ion, consider experiment 2 and experiment 3. Because in these two experiments, concentration of methanol are constant, right? So let me apply the formula. V01 upon V02 equals to concentration of A01 over concentration of A02 power m, and m is basically the order of reaction. V0 is initial rate, A0 is initial concentration. So this is V01, and this is V02. A01 is 0.015, and then 0.020. So it's basically 0.75 equals to 0.75 power m. So m is going to be the first order reaction. So with respect to hydrogen ion, it is first order reaction. All right. Let's talk about for methanol. Methanol is a very straightforward case. as you can see in the data, the concentration of methanol in experiment 2 and 3 are constant. On the other hand, rate of reaction changes, which means rate has nothing to do with the concentration of methanol, which means rate of reaction is independent to the concentration of methanol, and therefore with respect to methanol it is zero order reaction. In experiment 2 and 3, concentration of methanol are constant while rate of reaction changes. Hence, rate is independent of the concentration of methanol. Thus, it is zero order. Let's move on to the next. In a separate experiment, a large excess of methanol and hydrogen ion are added to a solution containing a known concentration of propanone. Since we know the concentration of propanone and we are taking methanol and hydrogen ion in excess, which means we need to keep the concentration of both these substances constant so that we can find the order of reaction with respect to propanone. And for that, examiner has given us a graph in which concentration of propanone varies over time. So it's a decreasing gradient, by the way, guys, right? We have discussed this in class. Use figure 2.2 to show how under these conditions reaction 1 is first order with respect to propanone. Since examiner has given us an information about the order of reaction, which means we need to look after a constant half-life in this scenario. Because whenever we have concentration and time ka data, we need to look after, we need to consider the constant half-life scenario. So let's talk about this now. Initial line at 50. All right, so from here to here, let me count the first half-life. This is 100, 10, 20, 30, 40, 50, 60, 70. So the first half-life is 170 seconds, right? Now this value is 50, half it, this is 20, 22, 24, 26, 28, 22, 24, 26, 28, and then 30. So somewhere around here, 20, 24, somewhere here. Exactly the center line, okay? Now from here to here, the time is 10, 20, 30, 3:30. So second half-life, 3:30 minus the initial value, which is 170. So 330 and minus 170 is going to be 330 minus 170 is going to be 160 seconds. That's almost a constant half-life is observed, right? So from, let me write it down. From 100% to 50%, concentration of propanone, half-life is 170 seconds. From 50% to 25%, concentration of propanone half-life is 160 seconds, hence almost constant half-life is observed. Order of reaction is said to be 1. Is said to be first order. All right. Oh. Next part of the question is, propanone also reacts with acidified cyanide ions to form hydroxynitrile compound B as shown by reaction 2. We have done this reaction in A2. We have done this reaction in A1 also. I've told you in the class, whenever cyanide and hydroxide are attached to the same carbon, such class of compounds are called cyanohydrins. All right. And this is ketone. Ketone always undergoes nucleophilic addition reaction. All right. So this is nucleophilic addition reaction ki example. The following rate equation is determined for reaction 2. Now, with respect to propanone, order is first. With respect to hydrogen, order is first. If propanone has no power, I'll take 1. Same here, I'll take 1 because there is no power, right? So if koi power nahi hoti to first lete hain, which means with respect to propanone, the order of reaction of propanone and hydrogen ion is first. 4 possible mechanisms for reaction 2 are shown in table 2.2. Okay. All right. So from my perspective, mechanism 4 is going to be the right answer, because mechanism 4 is consistent with this rate equation. Since rate equation has only propanone and hydrogen ion, which means both propanone and hydrogen ion are involved in the slow step reaction. So here, both propanone and hydrogen ion are not involved in the slow step, not involved in the slow step, not involved in the slow step, but involved in the slow step, right? Which means mechanism 4 is consistent with the rate equation. Consistent all right, because both propanone and hydrogen ion are involved in the slow step reaction. and both have first order reaction. Thus, concentration of propanone and hydrogen ion are changes. All right. Next, carboxylic acid C4H8O3 forms when B is hydrolyzed under hot acidic condition. All right, seems interesting. Hot acidic condition and acid hydrolysis, I mean to say, right? So compound C, where is compound C, by the way? Oh, my bad. Okay, when B is hydrolyzed, so when B is hydrolyzed under acidic condition, obviously the entire segment of this molecule will remain as it is, but this CN under acid hydrolysis will turn to CWH. So that's an easy task. We have done that. So CH3 will remain as it is. This CH3 will remain as it is. This OH will remain as it is. So this part of the molecule will remain as it is. Now CN under acid hydrolysis will turn to CWH. That's interesting. The pKa of C is 3.9. Calculate the pH of 0.5 mole per dm cube solution C. Since it is a carboxylic acid, it is a weak acid. So in order to calculate the pH of any weak acid, I'm going to use this formula, if you remember. pH equals to minus log under root Ka times concentration of this acid, which is represented by Ha. Now, in order to calculate Ka, examiner has given pK value. So use this pK value to find the value of Ka. This is 3.95 equals to minus log Ka. So value of Ka from here is going to be, let me calculate, shift log minus 3.95 to 1.2 or 1.12 to 0 into 10 to the power minus 4 mole per dm cube. Now plug in these values in this formula as it is. 1.1220 into 10 to the power minus 4. Concentration of acid is given, which is 0.5. All right. So the pH of this solution C is going to be multiply 0.500 under root answer negative log answer. It's 2.311. 311, my bad, 2.133. So 2.13. All right. Solution C can be used to form buffer solution D. Define buffer solution. A solution which maintain its pH fairly constant even upon the addition of small amount of acid or alkali. Whew. Next part of the question, buffer solution D is made when 20 cm cube of 1 mole per dm cube NaOH is added to 100 cm cube of 0.5 mole per dm cube solution C. Now this is solution C. All right. This is solution C, and it is reacting with NaOH, converting into salt and water. So let me write the equation. CH3 taken to COH, CWH plus NaOH, converting into salt and water. All right. Let me find out the initial moles of acid and alkali. So using this information, I can find the value of moles of NaOH. So it's 20 into 1 divided by 1000. So moles of NaOH is going to be 0.02. All right. Now using this value and this value, I can find the moles of acid. Moles of solution C. So it's 100 into 0.5 divided by 1000. So it's going to be how much? 0.05 moles. Final moles. See, NaOH is the limiting reactant. Obviously, it will consume fully during the reaction. And obviously, due to 1:1 ratio, if 0.02 moles react, obviously 0.02 moles of salt and water are also formed because of 1:1 ratio. I'm going to ignore water in the buffer solution. I'm going to use only salt and acid. All right. The initial amount of acid is 0.05. And because of 1:1 ratio, 0.02 moles are reacted. So the amount remaining after the reaction would be 0.03. See, the total volume of this buffer solution will remain same, which is why that volume will cancel out in the Henderson equation. So we don't need to convert these moles into concentration, all right? Because total volume is same, it will cancel out in the Henderson equation. So let me try the Henderson equation straight away. pH equals to pK minus log concentration of acid over concentration of salt. Since pK की value is given, which is 3.95 minus log concentration of acid. Acid is 0.03. I've told you these moles are actually the concentration because the total volume of acid and salt would be same in this whole scenario, right? So it will cancel out in this Henderson equation. So we don't need to write we don't need to convert moles into concentration. So 0.02. So pH is going to be how much? 3.77. So that's the end of question number 2. Again, it's a lengthy question. Question number 3. Fe2 plus and Fe3 plus ions are able to form a variety of complexes with different species. Define complex. It is a chemical species in which transition metal ion or atom is surrounded by a set of ligand through dative bond. All right. Table 3.1 gives some details of different complexes Fe2 plus and Fe3 plus. Complete table 3.1. If transition metal ion is Fe2 plus, ligand is ammonia, coordination by 6, the formula is going to be like this. Fe NH3 taken 6 and whole charge becomes 2 plus. यहाँ लिखा है 2 plus. Okay. Now the complex is here, which means in this complex ion, the oxidation state of iron is 2 plus again. The ligand is going to be chloride ion, and the coordination number is 4 because 4 ligands are attached to the transition metal ion. Now in this complex ion, the oxidation state of iron is 3 plus because ethylene diamine is a neutral ligand. Coordination number is 6. Coordination number is basically the number of dative bonds. Since 3 bidentate ligands are attached to the transition metal ion, which means in total it can form 6 dative bonds, which is why I will write 6 instead of 3. All right. Complete figure 3.1 to show the splitting of the d orbitals in a tetrahedral complex. So in a tetrahedral complex, we have degenerate d orbitals. Degenerate d orbital means equal energy orbitals. And when tetrahedral arrangement is established, obviously these degenerate d orbital is split into 2 different set of energy groups, right? The lower energy group is called Eg, which contain dx square dash y square and dz square. And the higher energy group is now T2G, which contain dxy, dxz, and dyz. So the degenerate d orbital, the equal energy orbital, is split into 2 different set of energy groups. One is lower energy, one is higher energy. Lower energy has dx square minus y square and dz square. Dx square dash y square, you can also say that. dxyz, dyz, dxz has the higher energy set of orbitals. All right. I hope it makes sense to you. We have done this in class, both octahedral and tetrahedral, and I've given you the reason also. Why these groups are flipped in tetrahedral complexes? Because ligands and orbitals exist between the axes, so they will experience more repulsion, which is why they will settle as higher energy group. Yes, on the axis होते हैं ligands in tetrahedral complexes exist between the axes, which is why they will experience less repulsion, so they will settle as a lower energy group. All right, we have discussed all these things in the class. All right, hope you remember that. Oh my goodness. Table 3.2 gives details of some complexes of Fe3 plus. Okay, this complex has a violet color with a stability constant of 1. This complex has red color with a stability constant of 1.4 times 10 to the power 2. The higher value of stability constant indicates that the complexes which are formed through thiocyanide ions are more favorable and stable as the ones which are formed through water molecule, which means this complex is more stable than this. Now look at this complex. It has fluoride ion. Its color is colorless and its K-step value is much higher, which means this complex is more stable than thiocyanide 1, and thiocyanide 1 is more stable than Fe2 plus. So from these K-step values, I conclude one thing. Okay, Fe, H2O taken 5, 2 plus are the most stable ones. Then this one. And then this one. This is the stability constant, stability of complex criteria. Explain the reason for the difference in the color of the two complexes, this and this. So when different ligands have different strength, have different strength, so they will have different splitting energy. So due to DD electronic transition, they will absorb different energy for electron promotion. At different frequency. Hence, different complementary color is observed. All right. Whew. Write an expression for the case step of this complex. First of all, let me write down the equation. This is FeH2O taken 6,3 plus thiocyanidine undergoes ligand substitution reaction that indicates thiocyanidine is a stronger ligand than water. It will substitute one water molecule and obviously it will turn to this complex. Now, on the basis of this equation, I will write the case step criteria here. So concentration of product over concentration of reactant. Charge has to be inside the bracket, if you remember. And then concentration of thiocyanidine. While writing case step, I will ignore water molecule because they will remain in excess condition. So whatever in excess, we need to neglect it. Okay. So that's the case step. Oh God. Use information in table 3.2 to calculate the value of the equilibrium constant Kc for the following reaction. Kc, examiner is looking for the Kc. Examiner is looking for the Kc for this equilibrium reaction. Whew. Now, this concept is extremely tricky. Okay, first of all, I need to make this equation and then this equation and then this equation has to be, I have to flip this. Okay, I've got the idea, but let me tell you one thing. Let me discuss this in detail. Otherwise, you are not going to get the concept. Let me discuss this. See, here thiocyanide ion complex has to be on the product side, whereas in this equation, it has to be on the reactant side, which means I need to flip this equation. All right. If I'll flip this equation, obviously this K step is going to be 1 over K step. I hope it makes sense to you. Okay. So I need to flip this equation. So this K step is going to be how much? 1 over K step, because I'm flipping the equation. Why I'm flipping the equation? Because this complex here on the reactant side, while this complex here on the present on the reactants product side. So I need to flip the equation, guys. I hope it makes sense to you. So I need to flip this equation. Okay. So this is Fe H2O taken 5 SCN 2 plus water, reversible arrow. It's a reversible arrow, yes. Reversible arrow. So it's going to be Fe H2O taken 6 3 plus SCN minus. Also, it is the reverse reaction. So it's basically K step. Reverse of first equation. So it is 1 over K step thiocyanidine. Okay. Now this is the second step. I will write it down here as it is. Fe H2O taken 6 3 plus fluoridine, reversible sign. Fe H2O taken 5 fluoride 2 plus water molecule. And since this is a forward reaction, so its stability constant value will remain as it is. K step for fluoridine will remain as it is, which we need to find out. Okay. Let me merge these two equations. We know that these two cancel out with each other. Yeah. So the final equation would be like this. All right. And ये exactly वही equation है जो examiner ने मुझे यहाँ बना के दी. I hope it makes sense to you. How did I get this whole equation and what the whole concept? Now we need to find out the value of Kc. So Kc is always equals to K step Kc is always equals to this and that, right? So it's basically 1 over K steps thiocyanidines into K step fluoridines. So Kc equals to 1 over K step thiocyanidine. K step thiocyanidine. Thiocyanidines exist in this complex and its value is 1.4 into 10 to the power 2. Let me write it down here. 1.4 times 10 to the power 2 into K step fluoride. K step fluoride. Fluoride is given in here. and its value is 2.4 into 10 to the power 5. So Kc is going to be like this: 2.4 into 10 to the power 5 divided by 1.4 into 10 to the power 2. So Kc की value is going to be 1714.28. So that's the answer, by the way. That's the answer. So I need to write it down, this thing here. Oh, I cannot adjust this value here. Let me write it. Kc equals to 1 over K step thiocyanidine into K step fluoridine. 1 over 1.4 into 10 to the power 2 into 2.4 into 10 to the power 5. So Kc is equals to 2.4 into 10 to the power 5 divided by 1.4 into 10 to the power 2. So the value of Kc in this scenario is going to be 1714.28, and that's my answer. I hope it makes sense to you. Now, a few drops of Kf are added to the solution this, followed by a few drops of potassium thiocyanide. Use information in the table. Okay. Describe any observation after each addition. Explain your answer. Now, when I add fluoridines, obviously reaction favors towards right hand side more favorably, because K step of this complex is more as compared to this one, which means this complex is more stable, which means color changes from violet to colorless. On adding potassium fluoride, concentration of fluoridine increases. Equilibrium favors towards right hand side. Color changes from violet to colorless. I hope it makes sense to you. I'm talking about this equation. So when you add fluoridine, ligand substitution reaction takes place. All right. So this color is violet. This color is colorless. When you add fluoridines, equilibrium favors towards right hand side. This complex is formed. Obviously, it shows colorless. Now, when you add thiocyanidine in this complex, no reaction takes place, because this complex is more stable than the thiocyanidines ones, right? So never reaction never gonna takes place, because एक more stable complex से एक less stable complex कभी भी नहीं बनता. All right. Since FeH2O taken 5 SCN 2 plus is more stable Then, oh, my bad. Oh, fluoride. Then, so no color changes. Solution will remain colorless. So no reaction occur. यहाँ लिख देते हैं, so no reaction occur. Solution will remain colorless. I hope it makes sense to you. My goodness. Oh my God. Part C. Hydrated compound J contain the green complex ion. Okay. The value of X can be determined by titration of a sample of J with acidified magnate 7 ions. Magnate 7 ions oxidizes C2O4 2 negative ions in acidic solution. By the way, we have discussed this whole scenario in the class. This is ethane dioetine, which is a reducing agent. This is magnate 7 ions, which is the oxidizing agent. And obviously, it's a redox reaction. All right. Write half equations for the oxidation of C2O4 ion and reduction of magnate ions. So let's make C2O4 2 minus. It is converting into carbon dioxide. How would I know? Because it's given in this equation that C2O4 is converting into carbon dioxide. Now, first of all, balance the number of carbon atoms. So we put 2 here. We have 4 oxygen atom here, 4 oxygen atom here. We have 2 minus charge here. So to balance the charge, I will use 2 electron here. I'm using actually ion electron rules. All right. Similarly, MnO4 negative ions is converting into Mn2 plus ions. Now, according to the first ion electron rule, manganese is balanced. In order to balance 4 oxygen atom, I will use 4 water molecule here. We have 8 hydrogen atoms here, so I will use 8 hydrogen ions here. The total net charge is 2 plus on the product side, whereas the total net charge on the reactant side is 7 plus. How come? This is 8 plus and this is minus 1 becomes plus 7. So to convert plus 7 into 2 plus, I will use 5 electrons here. And when I balance the number of electrons, obviously these number of electrons cancel out with each other and I'll get this equation now. Okay. A student prepare a solution containing 0.1 gram of J. Okay. This is 0.1 gram of J. The student titre this much concentration of MnO4 using this volume. Calculate the value of K in this complex. The MR of this green complex is given. Okay. That's the trickiest part. How many marks we have? 4. Oh, it's fine. Makes sense. It's a lengthy calculation, by the way. Now, in the first step, first of all, find the moles of magnate 7 ions. The concentration is given, which is 0.02. The volume is given, which is 12.2. Divide by 1000. So I'll get 1.64 into 10 to the power minus 4 molar. Okay. Molar means mole per dm cube. Now, in the second step, equation is given. And in that equation, we have a molar ratio between these two substances. This is 2:5 ratio, according to this diagram, this equation. Okay. So if we have 1.64 into 10 to the power minus 4 molar, moles of ethane dioetine would be 6.1 into 10 to the power minus 4 moles. We have a salt, we have a formula of salt which is K3FeC2O4 taken 3 dot XH2O. In this salt we have 3 ethane dioetines. So this is 1 mole, this is 3 mole. If we have 6.1 into 10 to the power minus 3 moles, so how much moles of salt? So moles of salt is going to minus, my bad, this is not 3, this is minus 4. Minus 4 moles. So I know the moles of salt and I know the mass. I can find the value of MR of this salt. Mass is 0.1, moles is 2.03 into 10 to the power minus 4. So the MR of salt is going to be 491.80. See the MR of this part of the molecule is given, which is 437.8 plus 18x, which shows water, equals to 491.80, which is your MR. So 18x equals to 54.7, then x equals to 54.7 divided by 18, then x equals to 3.03, and nearest whole number mein show karna hai, so I'm going to write only 3. So that's the end of question number 3. All right. All right, so let's move on to the next question. Question number 4. State the difference in the basicities of ammonia, propanamide, and propylamine. By the way, this is aliphatic amine, and aliphatic amine are stronger base than ammonia and propanamide. So the strongest base is propylamine. And the weakest base is propanamide. By the way, all amides are neutral, all right? That's what we have discussed in the theory classes. And obviously, this is ammonia. आप यहाँ नाम भी लिख सकते हैं. It doesn't make any difference. Let me explain why. Amides are neutral because lone pair of nitrogen is delocalized with pi bond of oxygen. Hence, lone pair is not available for protonation. All right. propylamine is the strongest base. So due to positive inductive effect of alkyl group, electronic density on nitrogen atom increases. So lone pair is easily available for protonation. Ammonia can also accept proton as it has lone pair. Obviously, both propylamine and lone ammonia has lone pair, but the availability of lone pair in propylamine has greater affinity for the protonation as compared to ammonia because of the positive inductive effect of electron donating alkyl. Next part B, figure 4.1 shows two different ways to synthesize propylamine. This is propylamine. Identify compounds K and L and reagent M for figure 1.2. Okay, amides are formed when acyl halides react with ammonia. So K is going to be the acyl halide. All right, and M is basically the reducing agent. Because I'm reducing amide into amine, I'm reducing nitrile into amine. So L is going to be the nitrile thing because I'm reacting it with potassium cyanide. So in order to make propanamide, I will use propanoyl chloride as an acyl halide, okay? So K is CH3, CH2, CO, Cl, propanoyl chloride. L is nitrile, so it's going to be cyanoethane, also called propane nitrile, which is CH3, CH2, M is basically reducing agent, and reducing agent is going to be lithium aluminum hydride in ether, in dry ether. Instead of using lithium aluminum hydride, you can use hydrogen gas in the presence of palladium catalyst under heat. Okay, I hope it makes sense to you. That's an easy part of the question. Okay, compound N is shown in figure 4.2. Basically, this is amide. This is also amide. So compound N is treated with an excess of concentrated hydrochloric acid. So basically, it's acid hydrolysis, right? And it has to be in excess. So bond यहाँ से भी break करोगे, यहाँ से भी break करोगे. As per instruction, CO will get OH of water, COH. Obviously, this is going to be benzene, CH2, and NH is getting hydrogen of water, it will turn to NH2. All right. Now, last but not the least, this CO will get OH of water, this NH will get hydrogen of water. So obviously this CO will get OH of water, will turn to CWH, CH, NH is getting hydrogen of water, will turn to NH2. This is CH2 and this is OCH3. Okay, so these are the three different products when we treat it with concentrated hydrochloric acid in excess condition. So N undergoes complete hydrolysis to form three organic products. These are the three organic products. All right. The products are isolated from the reaction mixture at pH 4. pH 4 indicates that it is an acidic pH. Acidic environment है यहाँ पर. Draw the structure of the three organic products at pH 4. Assume CH3O group does NH2 will accept proton because of this acidic environment and will turn to salt. And obviously, the structural formula is given in a skeletal form, so I will write the skeletal structure. NH3 plus, Cl minus. CH3 CWH will remain as it is because carboxylic acid and acidic, they cannot react together. And obviously this compound has no effect on acidic condition, but it will accept proton and will turn to an ammonium salt. So it's going to be like this. CH, NH3 plus, Cl minus. This is CH2. This is OCH3. Okay, I hope it makes sense to you. D part. Compound P can be synthesized. Compound P can be synthesized from 1-methyl 4-nitrobenzene. So you can write 4-nitrotoluene. You can say that by the route shown in figure 4.3. Okay. So technically what's going on in this reaction scheme, NO2 is converting into NH2. Rest of the molecule will remain as it is. So I'm reducing NO2 into NH2. So I'll use tin concentrated HCl mixture. Condition is reflux. That reaction is going to be reduction. Then NH2 will turn to this. So basically it's an alkylation process. I'm going to use alkyl halide as a reagent. And CH3 will turn to CWH, which means it's going to be oxidation, KMnO4 in acidic medium, under heat, type of reaction is oxidation. Look, this is acid, this is ester, which means this process is going to be esterification. And for that, I'm going to use alcohol. CH3 taken to CH, CH2, CH2OH. So this alcohol is going to used in order to make this ester when treated with this compound. Okay. And obviously H2SO4 is acting as a catalyst under heat. Step 1 is a reduction reaction. Agreed. Complete the equation for this reduction. Reduction. All reducing agents are represented by nascent hydrogen like this. We have C7. Count hydrogens. 1, 2, 3, 4, 5, 6, 7 carbon. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. And 1 nitrogen. And obviously these two oxygen react with hydrogen, converting into 2 moles of water. Now how many hydrogen atoms here? 9 plus 4, 9, 10, 13. We have 7 hydrogen here. So 7, 8, 9, 10, 11, 12, 13. So I need to put 6 here. So this is your balanced chemical equation, guys. That's an easy one. That's not the difficult one. That's very, very easy. Complete table 4.1 to give details of each step synthesis as shown in this. Step 1, reagent. Tin concentrated HCl. Condition is reflux. Now in step 2, I'm going to use alkyl halide as a reagent under heat. Obviously, this is going to be substitution. Why? Nucleophilic substitution reaction. In fact, yahan se H, yahan se Cl, they will combine together to give you HCl. So it's dehydrohalogenation, you can say that. Okay, elimination or dehydrohalogenation. और ये यहाँ पर attach हो जाएगा. Okay. You can write elimination reaction also. You can say condensation reaction also. Okay. Number third is oxidation. So I'm using KMnO4 in the presence of acidic medium under heat. Type of reaction is oxidation. And the formation of ester is condensation. That's right, because water molecule is lost during the reaction. Whenever water molecule or HCl is lost, process is going to be condensation, right? We have discussed this thing in class in polymerization. So I'm going to write this structure as it is. CH3 taken to CH. अब चेक कीजिए, ये भी CH3, ये भी CH3, ये CH, ये CH2, ये भी CH2 और ये OH क्योंकि अल्कोहल होगा. CH2, CH2, OH. This is your reagent. Concentrated H2SO4 is your catalyst under heat. Okay. That's the end of question number 4. Question number 5. Cumene is an aromatic hydrocarbon used in the synthesis of useful chemicals. This cumene, since annihilation or takes in order to make this compound. Table 5 is the sp3 hybrid present molecule of cumene. Carbon atoms. These double bonded carbon atoms have sp2 hybridization. So 6 are the 3 carbon atoms, by the way, which shows dehybridization 1, 2, and 3. All right, that's an easy thing. Cumene can be synthesized via Friedel-Crafts alkylation, as I've told you earlier, as shown in figure 5.2. Name the mechanism involved in the Friedel-Crafts alkylation shown in this. Friedel-Crafts alkylation always undergoes electrophilic substitution reaction. The first step of the reaction forms is this cation. Identify a suitable reagent for the formation of this cation from 2-bromopropane. The suitable reagent is basically a Lewis catalyst. And that could be Br3. All right. ये होगा कुछ reaction. CH3 taken to CHBr plus AlBr3 gives you Br AlBr4 minus plus CH3 taken to CH positive. And guys, look at this. ये 2 degree carbocation है. All right. Yeah. Let's move on to the next part. include all relevant curly arrows and charges. That's an easy task. Pi bond is reacting with this electron deficient carbon, and as a result, a pi complex is formed. Each carbon has one hydrogen. Let me show that hydrogen. So हम as per my instructions, यहाँ से लेकर यहाँ तक we need to put dotted line and a plus charge. That's called pi complex. Now shifting of bond into the ring takes place in order to neutralize this positive charge of benzene ring. At the same time, hydrogen removes in the form of hydrogen ion. You will get this product. Okay. The Friedel-Crafts alkylation of benzene by 1-bromopropane also produces cumene as the major product. This carbocation formed in the first step. One thing. This is CH3, CH2, CH2, Br plus AlBr3, converting into AlBr4 minus plus CH3, CH2, CH2 plus. Guys, look at this. This is 1 degree carbocation. Okay. Now this 1 degree carbocation undergoes rearrangement. Why? Why? Because ये हाइड्रोजन यहां जाएगा और फिर ये CH3 में कन्वर्ट होगा और ये CH3 में कन्वर्ट होकर CH से अटैच हो जाएगा. This is CH and this is going to be CH3. This is your positive charge. This is 2 degree carbocation. And 2 degree carbocation is more stable than 1 degree carbocation, which is where rearrangement takes place. All right. And he's looking for the explanation. All right. तो हम लिखेंगे यहाँ CH3 taken 2 hold on CH3 CH2 CH2 positive is 1 degree carbocation. So it undergoes rearrangement to give CH3 taken to CH positive, which is 2 degree carbocation, which is more stable. Than 1 degree carbocation. Therefore, rearrangement takes place. All right. My goodness, that's part C. Cumene oxidizes in air to form phenol and propanone. Equation is given with a delta H value. Table 5.2 gives some relevant standard entropies of reaction 1. Calculate the standard entropy change of reaction 1. That's an easy task. Standard entropy change of system equals to summation of standard entropy of product minus summation of standard entropy of reactant. तो प्रोडक्ट आपके पास है फिनोल एंड प्रोपेनॉन, ठीक है। तो ये आपके रिएक्टेंट हैं, ओ सॉरी ये आपके प्रोडक्ट हैं, ये आपके रिएक्टेंट हैं। सो प्रोडक्ट में वैल्यूज प्लग इन कर लेते हैं, 146 प्लस 200, रिएक्टेंट में आपके पास है 278 प्लस 205, तो ये हो जाएगा आपके पास 346 माइनस 483. Standard entropy change of system is going to be minus 137. याद रखिएगा, entropy has a unit of joules, mole inverse, Kelvin inverse. All right. Show that reaction 1 is feasible at 25 degrees Celsius. By the way, 25 degrees Celsius, we need to convert it into Kelvin. So 25 plus 273 is going to be 298 Kelvin. In order to check the feasibility, I will use the Gibbs free energy change equation, which is like this: delta G naught equals to delta H naught R minus T delta S naught system. Let me plug in the values. Delta H R is given in the equation, minus 371. If delta HR is in kilojoules per mole, delta G has to be in kilojoules per mole, then it means entropy needs to be in minus temperature is 298 Kelvin. The entropy change of system is minus 137. To convert it into kilojoules, divide by 1000. So I believe delta G naught is going to be minus 330.174. All right, kilojoules per mole. Since the value is negative, which means reaction is spontaneous or feasible. All right. Oh my goodness, that's a very long question. Figure 5.4 shows two reactions of phenol. Okay. Phenol undergoes bromination in reaction 2. And obviously, when it undergoes bromination, it will turn to 2,4,6 tribromophenol. Because OH is an orthopara directing group, is an activating group, it increases the electronic density on both ortho and para position. So multiple substitution takes place with aqueous bromine. Okay. Since ये horizontal लिखा हुआ है तो मैं इसको horizontal ही लिख लेता हूँ, मसला नहीं है. It's not correct. I mean it's correct, but आप इसको examiner के perspective से दे दीजिए आंसर तो ज्यादा बेहतर है. This is going to be your OH. This is second carbon. This is sixth carbon. And this is fourth carbon. It doesn't make any difference. दोनों सही थे, but ये मैंने examiner ने जिस तरह से लिखा है उसी context में मैंने answer दिया. When this phenol reacts with R in the presence of NaOH and has a dye form, obviously R needs to be an aromatic amine. R needs to be an aromatic amine because azodyes are always formed through aromatic amines. State conditions for aqueous bromine. Condition aqueous, room temperature and pressure. Explanation. Well, let me read the question first. Explain why these conditions are different from those for the bromination of benzene. Benzene is less reactive. So it requires Lewis catalyst for bromination to form electrophile. OH group in phenol is an orthopara directing group. It increases the reactivity of phenol and increases the electronic density on orthopara position. Hence, multiple substitution takes place. Hence, reaction takes place at RT without catalyst. Okay. For the structure of organic compound Q, I've done that. Okay. Identify organic compound R. It must be an aromatic amine, so it has to be phenylamine. It has to be like this, phenylamine. Name the functional group that is formed in reaction 3, azo group or azodie, azo group, because this is going to be the azo group. The entire compound is called azodie. Okay. Okay. Next, the reaction of phenol with nitric acid produces a mixture of isomers with molecular formula this. Identify the two isomers that are produced in the largest quantity. Explain your answer. When phenol has OH group, which is an orthopara directing group. So if you react phenol with dilute nitric acid, obviously we'll get two different products. In fact, two different isomer. One is ortho isomer, ortho product, and the other one is para isomer or para product. So this is phenol. NO2 needs to be attached on the ortho position. Ortho position is 2 and 6. Up 2 pe laga and 6 pe laga, it doesn't make any difference. And the other one is para position. OH increases the electronic density on 2nd, 4th, and 5th carbon. Oh, my bad, not 5th, 6th carbon. That is the silliest mistake. On 6th carbon, due to positive inductive effect, hence two isomers are formed. Okay. By the way, para has more quantity than ortho because of the less steric hindrance. Para has greater amount due to less steric repulsion or less steric hindrance. We have discussed this steric hindrance in the class. Hope you remember that. Oh, next question. Question number 6. My bad. Malic anhydride is an unsaturated cyclic compound used in the formation of several polymers. Malic anhydride can be used to form malic acid and tartaric acid. So this is your malic anhydride, which is देखा जाए तो it is an ester, all right? इस तरह से देखें तो ester, इस तरह से देखें तो ester along with an alkene functional group. अब इस एस्टर की हाइड्रोलिसिस कर रहे हैं तो कार्बोक्सिलिक एसिड से डायोल बन रहा है. So इसका मतलब यहाँ पर एसिड हाइड्रोलिसिस हो रही है अंडर हीट और आर फॉर्म. Malic acid reacts with ethane 1,2-diol to form a condensation polymer. Draw a section of this polymer showing one repeating unit. The new functional group form should fully displayed. Okay. Malic acid is this. Let me write the structure of malic acid. COOH then COOH plus ethane 1,2-diol. This is CH2, and this is OH. Always remember, carboxylic acid always gives OH, alcohol gives H. Obviously, it will turn to water. यहाँ से OH remove होगा, यहाँ से H remove होगा. So I'll take the continuation, bond continuation. This is going to be oxygen. This is CH2, oxygen, and this is bond continuation. Plus N moles of water. And just water. Okay. And identify, and obviously this is going to be the ester linkage. Or polyester linkage. Identify a suitable reagent and condition for reaction 2. Reaction 2. See, CWH will remain as it is. CWH are not changing at all during the reaction. What is changing? Alkene will turn to diol. So alkene will turn to diol, and examiner is looking for the reagent and the condition. So it's going to be like this: cold, dilute, acidified, K1O4. Okay, my bad. That's tricky. Compound U can be formed from tartaric acid in two steps as shown in figure. तो स्टेप 1 में क्या हो रहा है कि ये टार्टेरिक एसिड है आपके पास, ये प्रोपेनॉन के साथ रिएक्शन कर रहा है इन स्टेप 1. और ये बन रहा है एक कंपाउंड टी. तो अगर नोट करेंगे तो ये कंपाउंड टी साइक्लिक रिंग की फॉर्म में एग्जिस्ट कर रहा है. तो ऑब्वियसली ठीक है, साइक्लिक रिंग की फॉर्म में एग्जिस्ट कर रहा है. ओके, ऑर्गेनिक केमिस्ट्री में इसको हम कंडेंसेशन भी कह सकते हैं, बिकॉज वाटर की एलिमिनेशन हो रही है. अगर आप नोट करें तो इसको ऑर्गेनिक केमिस्ट्री में कीटल फॉर्मेशन रिएक्शन भी कहते हैं. इट्स नॉट द पार्ट ऑफ योर कोर्स कीटल फॉर्मेशन रिएक्शन, लेकिन एग्जामिनर ने दे दिया है, सो पता होना चाहिए. ऑर्गेनिक केमिस्ट्री जो लोग पढ़ते हैं, जिनका सब्जेक्ट मेजर होता है, उनको पता होता है कि कीटल फॉर्मेशन रिएक्शन किसे कहते हैं. ऑलराइट, बट इन सिंपल वर्ड्स इट इज एलिमिनेशन और कंडेंसेशन रिएक्शन. ओके, और कीटल फॉर्मेशन रिएक्शन इफ यू नो ऑर्गेनिक इन डिटेल, क्योंकि यहाँ से OH यहाँ से H दोनों मिलकर बना रहे हैं वाटर, और ये ऑक्सीजन रह गया यहाँ पर. ठीक है, सो स्टेप 1 इज बेसिकली condensation reaction or elimination reaction. U can act as a bidentate ligand. Okay, what is mean by the term bidentate? Donate 2 lone pair to the transition metal ion so that two dative bonds are formed. Complete the three-dimensional. Three-dimensional means you need to make dotted line and pyramid. This is your dotted line and this is your pyramid. Same here, dotted line and pyramid. We have discussed this in class that bidentate ligand is represented by this symbol. So what we're going to do is, let's make this structure. Okay. When we have three bidentate ligands, I've told you in the class, we can have optical isomerism. All right. So in optical isomerism, both the structures are mirror images of each other. So both the structures are mirror images of each other, as you can see that. Okay. So stereoisomers means optical isomerism in this scenario because we have only three bidentate ligands. That's what we have discussed in the class. That's what you have written in the lecture. So whenever we have three bidentate ligands, isomerism is going to be optical and both the structures are mirror images of each other. Let's move on to the next part. My goodness. A student analysis an aromatic compound XC8H8O3 using NMR spectroscopy. That's a very, very, very analytical part because examiner has given not enough information in order to determine this structure. My God. I got one information, by the way, that it is an aromatic compound, which means it contains benzene ring. This is the first piece of information I've received from the question. Still, I don't know how many groups and what sort of groups are added with the aromatic ring. And we need to find out that. And for that, let's move on to the next part. Figure shows the carbon-13 NMR spectrum of a sample of X dissolved in D2O. Dissolve in D2O. By the way, for carbon-13, we don't need to add D2O because carbon and D2O has shown no affinity with each other. All right. So these are the number of peaks obtained. And from this spectrum, I conclude that we have total 8 chemical environments. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 chemical environments because we have 8 peaks. So one thing is confirmed, that compound X has 8 chemical environment, meaning it has 8 carbon atoms. This is the second piece of information I've collected. God, okay. Next, separate samples of X were analyzed using proton NMR spectroscopy. Table 6.1 gives information obtained from this analysis. When using CdCl3 as a solvent, total number of peaks is 6. So before adding D2O, we have 6 chemical environment. For carbon, we have 8. For proton, we have 6 chemical environment. After the addition of D2O, number of peaks will remain 4. 4 peaks are remaining, which means four chemical environment. इसका मतलब ये हुआ कि 2 फंक्शनल ग्रुप्स ऐसे थे जिन्होंने D2O के साथ रिएक्शन कर लिया. यहां से ये थर्ड पीस ऑफ इंफॉर्मेशन आई हमारे पास. two functional groups can treat with D2O। अब वो टू फंक्शनल ग्रुप्स कौन से हो सकते हैं? NH हो सकता है? नहीं, क्योंकि एग्जामिनर ने मुझे यहाँ स्ट्रक्चर में कोई NH2 नहीं दिया, नाइट्रोजन है ही नहीं। पॉसिबल है। क्या वो अल्कोहल हो सकता है या फिनोल हो सकता है? पॉसिबल है। तो दीज आर द टू पॉसिबिलिटीज जो कि इस कंपाउंड के लिए एग्जिस्ट कर सकती हैं। सो बेंजीन रिंग है, 8 कार्बन एटम्स हैं, दो फंक्शनल ग्रुप्स ऐसे हैं जो कि D2O से रिएक्शन कर रहे हैं, आइदर इट इज COOH और OH और बोथ। ठीक है। आइडेंटिफाई द नंबर ऑफ डिफरेंट कार्बन एटम एनवायरमेंट्स। तो 8 कार्बन एटम है। एक्सप्लेन व्हाई X dissolve in D2O before obtaining its proton NMR spectrum। ये फेयर कंपैरिजन के लिए किया जाता है। एक तो ये फेयर कंपैरिजन होता है बिटवीन प्रोटॉन एनएमआर एंड कार्बन 13 एनएमआर, और दूसरी बात ये कि it is used to map the carbon skeleton and provide a deuterium lock signal. That's very, very interesting. To map the carbon skeleton, because they are not, because they don't have any affinity with the D2O. And provide deuterium lock signal. This is the first point. Second point, functional groups undergoes substitution with D2O. Thus, functional group peak will disappear. And making a non-exchangeable proton signal. All right. So aromatic compound X gives yellow precipitate when it reacts with alkaline aqueous iodine. Oh my God, another piece of information. If it is given yellow precipitate with alkaline aqueous iodine, either it will have CH3CO group or CH3CHOH group. Look at this proton NMR spectrum. This thing. This peak appears at somewhere around 220 ppm, right? So at 220 ppm, we have carbonyl ki peak. So carbonyl could be ketone, carbonyl could be aldehyde. If it is aldehyde, obviously it's not going to show iodoform test. So this confirms that it must be ketone. Okay. So we have multiple sort of information First of all, benzene ring we have. Second thing, this CH3CO group is present. Third, we have COOH. Might be present. Or OH group might be present. Because these two functional groups can react with D2O. All right. So आपने पीछे देखा होगा कि D2O से रिएक्शन करने पे 2 पीक्स डिसअपियर हो गए, 6 के बजाय 4 रह गए। इसका मतलब या तो ये दोनों ग्रुप्स अवेलेबल हैं, या सिर्फ ये दो अवेलेबल हैं, या सिर्फ ये दो अवेलेबल हैं। So let me draw the structure, possible structure. First of all, let me draw this. This is COOH. This is COOH. Oh, my bad. COCH3. How many carbon atoms now? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbon atoms. Whereas we have only 8 carbon atoms. इसका मतलब this structure is not possible. We have 8. How many carbons now? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons है. So we have 9 carbon in this structure, which means this structure is wrong because carbon तो 8 होनी चाहिए. Second possibility. OH, COCH3, and then COOH. Let me count the carbon atom. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbon atom again. It's wrong because I'm looking for 8 carbon atoms because we have 8 chemical environments. इसका मतलब सिर्फ कार्बोक्सिलिक एसिड नहीं है, इसका मतलब कार्बोक्सिलिक एसिड और फिनोल भी नहीं है. Let me draw another structure. ये मैंने ऑर्थो पोजीशन के ऊपर ग्रुप लगाया. Carbon count करो. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 carbon atoms here. So carbon satisfied. Let's talk about oxygen. Oxygen are not satisfied because we have 2 oxygen in this formula. An examiner has given us 3 oxygen atoms. So 1 oxygen left. Remember, 1 oxygen left. How many hydrogen atoms? 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogen atoms. And how many hydrogen atoms we have? 8 hydrogen atoms. 8 carbon atoms. These two possibilities are satisfied. Oxygen is not satisfied. What we can do is, I'll write another OH here. Because beta, अगर सिर्फ ये एक होता तो सिर्फ एक पीक डिसअपियर होगी ना इसकी D2O के साथ. Examiner was saying कि 2 peaks disappear हुई हैं after treating the sample with D2O. That means 2 OH group needs to be there. Let me check the number of carbon atoms now. 1, 2, 3, 4, 5, 6, 7, 8. Carbon satisfied. Hydrogen count करते हैं. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen satisfied. Oxygen 1, 2, 3. Oxygen satisfied. So that is the structure of this compound, C8H8O3. All right. I hope it makes sense to you. ये जो कुछ मैंने लिखा है ये सब आप यहाँ पर लिख सकते हैं. ये सारी पॉसिबिलिटीज, ये सारी चीजें बता सकते हैं. आप बता सकते हैं कि ये सारे के सारे ग्रुप्स जो हैं वो आइडोफॉर्म का टेस्ट पॉजिटिव देंगे. ऑलराइट. आप ये भी बता सकते हैं कि ये भी लिख के दीजिएगा ये वाली इंफॉर्मेशन कि भाई एल्डिहाइड कार्बोनाइल एग्जिस्ट करा बिकॉज 220 ppm के ऊपर पीक अपीयर हुई है. सो कार्बोनाइल 220 ppm. ओके. CH3 की पीक अपीयर है तो 0 से 50 ppm. अल्काइल नेक्स्ट टू कार्बोनाइल है. So alkyl next to carbonyl is this 3665 ppm. तो ये आप सब लिख के देंगे. बेंजीन रिंग है और बेंजीन रिंग में C6H3 है. So benzene ring is basically arenes. Arenes 110 से 160 ppm. So all these data and this sort of analysis needs to be included here in these lines in order to get the full marks. So that's the end of this